Imagine you're diagnosed with a disease that nobody's ever heard before. A doctor doesn't know what to do, they don't have a procedure, there's no cure for it. And the only thing they can do in this case is take it to the lab and spend 10 years trying to figure out the cure. By the way, this will also cost them a couple $100 million, and the process looks something like this. They'll try maybe 10,000 potential drugs, and maybe, if they're lucky, get one in the outcome. So obviously this process is failing you in a lot of ways and failing society financially. So you might look to other methods, and one thing that we've tried is simulation. So what if we could just simulate this research process and find the drug just through a computer? And what we found is that not even the most sophisticated machines that we've ever invented, supercomputers, have been even close to be able to comprehending these sort of problems. With the recent invention of quantum computers, we've actually had a glimpse at what the solution to this problem might be. To understand why, think about asking a cat to understand multivariate calculus. Their brains are not wired that way. They literally cannot have the capacity to understand those ideas. Likewise, in a supercomputer, the limiting factor is literally the hardware. That computer cannot operate on those types of problems. This is where the quantum computers come in. And so a couple weeks ago, I actually had the opportunity to visit and see these quantum computers up close. So I flew down to San Francisco, and I got to visit Rigetti. And actually standing beside a quantum computer was an amazing experience in and of itself. Don't think I've ever been in a room worth that much money. But over the next few days, we were able to work on an actual simulation project with the theorists and engineers there. And what we came up with is this. So this is the code for our project that actually simulates a helium hydride molecule. It's a very simple molecule, but it's actually not as simple as you might think. And essentially what you're seeing there in that graph is the energy as a function of the bond length and the bond angles within that molecule. And these are kind of some weird terms, but essentially what we're doing here is using quantum machine learning to simulate this helium hydride molecule. To understand exactly what's going on, think about two helium hydride molecules. They're just two atoms each. And then what happens when they collide? So this also gets really complicated really quickly. But you can kind of break it down into something like this, where you have a simple system of two protons, just two spherical orbs, orbiting around each other. And there's also a couple electrons in there as well. What you want to do to find the interactions is essentially just find the total energy of that system. So if you can find what is called the Hamiltonian, or just an equation that represents that energy, you can find out how that molecule will interact with other molecules. And so we have the formula for the Hamiltonian in the top left. It looks pretty complicated, but if you just look at these 5 summation terms, these are just finding individual energies of different parts of the molecule. So you can kind of think about it like the first one might be the sum of the energy in the bond between the protons, and then the next one might be the bonds between the electrons and the protons, and things like that. And eventually you'll find the energy of that molecule and thus how it will interact with other molecules. So to simplify this, think about a plane. A plane is a really complex system with a lot of small moving parts, and all of those parts work together to keep the plane in motion. But what we care about in this case is how the plane will interact with, say, a gust of wind. To figure out how that works, we need to figure out how the gust of wind will interact with each individual part, and then that will tell us what the net effect on the system is. So we have molecular simulation, but what's the catch? So we were simulating helium hydride, which is a molecule consisting of just 2 atoms. If we want to think about what it would take to simulate drugs, let's look at amino acids, which are the building blocks for these proteins. So amino acids are molecules composed of about 12 to 15 atoms, and they're not too bad. We don't have the computation power to do that yet, but probably within the next couple of years, we'll be able to simulate something like an amino acid. Now, we have these polypeptide chains, or the primary structure of the proteins, and these are made up of about 50 to 100 amino acids. So already we're looking at a couple hundred atoms. This is well beyond the scope of what our quantum computers can do today, but we're actually advancing really quickly, and so I think this might happen within the next 5 years. These things come together, and about a dozen primary structures will form the secondary structure. These take some weird shapes. Sometimes they're like helices or sheets. But essentially, we're now looking at thousands and thousands of atoms all working together in the same system. The tertiary structure is one step before a protein. It's still not there yet, but it's made of about a dozen or so secondary structures. So we're literally looking at tens of thousands of atoms now. This is tens of thousands of times more complicated than the initial thing that we just simulated a couple weeks ago. And finally, the quaternary structure, which is composed of hundreds of thousands of atoms, like incomprehensible. We can't even understand how complicated these things are, but somehow these are the fundamentals of what make up our drugs today. So this is a little ways off. But once we get there, the implications of this are insane. Imagine that situation where you have this disease that nobody's ever heard of, and you walk into the hospital and they're like, hey, I know what to do. We take that drug, or we take that disease molecule, or whatever it is, and we put it into the quantum simulation, and in a matter of minutes, we could narrow it down to a single drug that actively and effectively targets that disease. So instead of spending decades of research and hundreds of millions of dollars, we'll be able to do this in a matter of minutes. This is what I'm trying to do right now with quantum machine learning. And so our project last weekend and what I'm working on right now is the first step in that direction. Thank you.